Okay. Here we go. Let's talk about the polar coordinate system. Okay, so I'm going to actually start the notes down here. I know that's kind of weird, but then I'm going to put the coordinates up here. We're going to do stuff up here for some practice with this. Okay.
Should we put this on the paper or should it be on a separate piece?
I'd say put it on the paper. That's my opinion. I have a hole punch. I have a hole punch too, if you like, or if you want to staple it into your paper or something like that. That's fine. But okay, so the polar coordinate system is an alternative way to locate points in a two-dimensional plane. Okay, so all of your life, right? You've thought perhaps that the only way to locate things in two dimensions, right, is to use our good old-fashioned rectangular coordinate system, right, using the x and y coordinates, okay? X coordinates having us go left and right, the y coordinates having us go up and down, and then that locates any single point in a two-dimensional plane, okay? However, that's not the only way that we need to go about doing that, right? So you think so that rectangular coordinates, maybe you could think of that as Battleship, right? Battleship, if you ever played Battleship before, you have the letters and the numbers and you locate, that's how you tell the other person where you're going to shoot stuff and all that, okay? But another coordinate system that we have we're going to introduce right here is the polar coordinate system. Okay, so what's the setup here? How does it work, right? So the origin, okay, is now known as the pole. P-O-L-E. Okay? So you can see here, if we look at our graph paper real briefly, okay, you can see where the pole is, right? I mean, here you can think about, imagine mapping this onto our normal rectangle, our more usual, typical rectangular coordinate system, right? You can see here, this would be the pole, right here, okay, at the very center of our polar coordinate. Okay, graphs. There's the x-axis. If we were to, again, think about rectangular coordinates, and the y-axis would be something like this, right? So you can see the rectangular coordinates in there, okay? See the rectangular graphs in there and stuff like that. But you'll see that we have different grids here because of how we're going to be locating points, okay? The x-axis, I should say the positive part, or maybe I'll say just x greater than 0 part. No, I won't put the part where I'll just do x. So the part greater than 0, okay, so the positive part of the x-axis, it's now known as the polar axis. Okay? And we graph points as follows. Okay. So we're in a two-dimensional space, right? In the past, when we were graphing things in two dimensions, we needed two numbers, right? An x-coordinate and a y-coordinate. All right? The number of numbers is not going to change, right? The very fact that it's two-dimensional requires that we have two numbers to locate a point, right? You can't do locations of points in two dimensions using a single number, right? It just doesn't work. You have to have two numbers to locate a point in two dimensions, right? In one dimension, you need one number. In three dimensions, you need three numbers, right? In four dimensions, you need a good imagination because I don't know what that would look like. But you need four numbers, though, okay? So here's how we're going to graph points. All right, so we're going to have our pole, okay, and then the polar axis. Okay. Okay. And then here's where the numbers come in, okay? We're going to, from the polar axis, we are going to rotate a certain angle theta. Okay. And then from the pole, we are going to move out a certain distance, r. And so our coordinates will be r comma theta. Okay. The coordinate will be r comma theta. So no longer is the first number going to be how you move left and right, and the second number going to be how you move up and down. Instead, it will be how much you rotate for the second number, and the first number will be then how far you extend in that direction. Okay, how far out you go in that direction. So r is for like radius, right?
Is that the line?
Yeah, that is the distance. That distance r there. And that's how we're going to locate points, okay? So we are fundamentally changing how we graph things, okay? And so with that fundamental change, well, we're going to have this whole entirely different family of graphs that we can now create based off of this kind of method. Okay? And so this is like gonna fundamentally changes, the way we think about graphing and stuff like that. So it's gonna be uncomfortable, probably at first. But why?
Yeah.
Great question. So great question. So where do you think we use something like this? In fact, it is in our it is real world for sure.
Radar?
Not radar. So it's called polar coordinates. Where do we have a pole in our real life? The North Pole and the South Pole, right? So have you ever seen a map? Have you ever seen a map of the not time zones because those aren't straight lines? Have you ever seen a map of the world from the perspective of the North Pole or the South Pole? Yeah. That's this, isn't it?
Stupid.
Okay. What are these like kind of like radius or not the radius? What are these like long lines like this? It is the longitude, and then these circles are the what? Latitudes. Yes. So this is real life. Okay. This is like
Cartographer.
this is two-dimensional plotting. Okay. You can think of this as like on the globe, right? So this allows us to two-dimensionally locate coordinates on a sphere, right? I mean, we're able to do this using our longitude and latitude and stuff like that. So this is absolutely, realistic and useful and stuff like that. Okay, so yeah, let's and I mean, isn't the pole, at the pole, right, is where we have like the 0 degrees, or no, I guess it's never mind. The equator is 0 degrees, so it's like 90 degrees, or is that what it goes up to for the latitude? I'm not sure, but anyway, so. You get the idea there, okay? This is like looking at the Earth from the South Pole or from the North Pole kind of thing, and you get this kind of coordinate system. Okay, so let's plot some points, just for some practice, right? Because this is what you guys did way back when you first learned about rectangular coordinates. You start by just plotting some points, okay? And some weird things are going to show up here. So, and I'll highlight those when we see them because you might not be able to see the weirdness. Or maybe you think this is all weird. Okay, so key idea here. Locate theta first, then plot using r. Okay, so locate theta first, then plot using r. Okay, so we're going to find the second number first, use the second coordinate first, and then use the first number in the coordinates. Okay, so let's just get some practice in here. So let's do 2 comma pi over 3. Okay, 2 comma pi over 3. We're going to locate that point. Okay, again, remember 2 is our r, pi over 3 is our theta, and so we're going to look here on our coordinate system. And let's just call this point A or something like that, just to make it a little bit easier. Okay, so we'll go to our coordinate plane here, and I'm going to locate. Well, here's our polar axis, and from our polar axis, if we rotate pi over 3, we're going to be somewhere along this line right here. Right, this line right here is pi over 3. Okay, but then from our pole, from the pole here, we are to extend 2. Okay, now let's see. How did I do this before? Okay, I'm going to count each one of these rings as 1. So that's 1. That's ring of 2, 3, 4, 5, 6, 7, and 8. Okay, we'll do it that way. Okay, so each ring will count as a radius of, a unit radius kind of thing. So a radius of 1, and then 2 radiuses, 3 radiuses, 4 radiuses, 5 radiuses. You get the idea, so on and so forth. I will try. I can't really fit everything there. You need to see this?
Yeah.
It's just every ring you're going to label as 1, 2, 3, 4, 5, 6, 7, 8. Okay.
Oh, okay.
Yeah. Again, these are just the distances. So this ring, any point on this ring will be 1 r, right? 1 radius value from the center, right? This ring, anything on this ring will be 2 radiuses, right? Or 3, 4, 5, so on and so forth. You get the idea, right? So, again, pi over 3, there's our pi over 3, and we're going to go out towards that pi over 3, 1, 2 radiuses, and so there's our point A. Right there. Okay? Along that pi over 3 angle, 2 measures out there, 2 units out towards it. Okay? Let's try another one. Let's do 3 comma negative pi over 6. Okay, now, negative pi over 6 means we're going to rotate which direction? We're going to go, clockwise, right? Positive pi over 3, we go counterclockwise. So negative pi over 6, we're going to rotate pi over 6 in the clockwise directions, which means which angle will we be kind of going along here? So it's coterminal with 11 pi over 6. So we're going to be looking at this right here. And again, it's a positive 3r value. So from our pole, count out 1, 2, 3 rings, and there's our point B. Okay? Word. All right. And let's plot another point here, C, and let's call it 3 comma 11 pi over 6. Okay? Now, where will point C be located? The same point as point B. Okay, right? Because now we're talking positive 11 pi over 6. So again, from our polar axis, we will rotate in the counterclockwise direction, 11 pi over 6. Oh, there's 11 pi over 6. We're going to be along this line. We're going to go 3 in that direction. So this is also point C as well. Okay, so that's different. We have 2 coordinates, different coordinates, but they locate the same point. Is that possible in rectangular coordinates, to have different coordinates that locate the same point in rectangular coordinates?
They're not really different,
Are the numbers the same?
they're just written down. Yeah.
But my point is, are the numbers the same? No. And that's unique, right? In rectangular coordinates,
Because it loops.
every coordinate, any combination of numbers in rectangular coordinates locates a unique point. All right? In polar coordinates, well, I can come up with an infinite number of coordinates that would locate that single point right there.
It doesn't really go on forever, though. It just loops.
Right. My point is that there unique to polar coordinates is that you can have different coordinates that locate the same point, which is not the same as rectangular. And again, you'll get some interesting results as a result of that. Okay. So, you guys try this. I'm going to give you 3 here to try. So let's locate point D at 4 comma 5 pi over 4. Locate point E at 8 comma negative pi. And let's locate point F at 0 comma 5 pi over 3. Okay, so go ahead, try those 3 there, and I'll do them in red on mine here. Five pi over 4 is what it is. Oh, 5 pi over 3 is the third one. Yeah, sorry. Theta is the angle. And then the number of rings you count out is the first number. It's r. So it's like, where are you on the rings is 5 pi over 3. And then how many rings you count out from the pole is the r. Where are you? That's right. I didn't mean to wear this sweatshirt, even though it did have polar on it. But now that it does, I'm like really convenient. I'm like, yeah.
You're so comfy on the inside, just soft.
Samantha's impressed. I can tell. The look on her face. It's not disgust. It's not. Do you want me to get? I was gonna say, you want me to have Simeon go down and get it for you? That way you don't have to like. Really? I mean, he can go. That way you can stay. I mean, because I'm assuming if it's your boot that's hurting you, and so walking more on it, I'm assuming it's probably not gonna help.
My legs are hurting.
That's weird. So they gave you a boot though. It was your knee that was bothering you,
It
right?
was my knee, but it's
now it's your.
I went to the MMI doctor yesterday during second walk and they like took some X-rays and did they moved my leg around and it's my calf muscle, so it's tied into my knee. So my calf muscles are hurting, so it's hurting my knee. So this is keeping my leg from in one position.
Keeping that calf from
But it's not used to the boot, so it's making it sore.
Oh, so like, okay, I gotcha. Well, yeah. Simeon, you want to go get her some ice, please? Thank you, Simeon.
Thank you.
Yeah, man.
It's just off.
Very cool. All right, here we go. There's D, E, and F. Okay. Unfortunately, with the way this graph paper is made, you'll see that they don't draw all these lines into the center, and that's not because that's the way it's supposed to be. It's because if they drew all these lines into the center, this would be kind of too smushed together. It would be too many lines in there, so they had to leave some space. Okay. But that being said, this is still 5 pi over 4, right? And you still want to count this ring and then this ring and then 3 and then 4 to get your, 0.4, 5 pi over 4 there. Okay. Now, any questions on those? I have 2 more I want to do, 2 more graphs, and then we're going to talk about converting. He converted. Okay, so we'll do negative 2 pi over 4, and we'll do negative 4 3 pi over 2. Okay, because we haven't talked about negative r values yet. We've only had positive r values. We've done positive and negative thetas, right? But we have not done negative r values yet. We've done positive but not negative. So how are we going to locate these points? Can we just not? It goes in exactly the opposite direction. Exactly right. So for the thetas, yes. For r, there is no rotation for r. So for g, okay, we'll locate pi over 4. So there's pi over 4, right? Okay. But instead of going towards the pi over 4, which is what happens when we have a positive r value, we're going to go in the exact opposite direction from pi over 4 because we have a negative r value. So instead of going towards pi over 4 to rings, we're going to go away from pi over 4 to rings. So 1, 2, and there is the location of g. So in other words, it's like we're going towards the 5 pi over 4, the exact opposite direction there. Okay? And then h, 3 pi over 2, so we'll rotate to 3 pi over 2, but instead of going towards the 3 pi over 2 for rings, we're going to go in the exact opposite direction. 1, 2, 3, 4, and there is h. Rotate to pi over 4 for the first one there, but because it's a negative r value, instead of going towards pi over 4 2 units, we're going to go in the exact opposite direction. And same thing for h. Okay? Questions on any of that? All right, so let me talk about then converting. I'm going to try and squeeze it in here next to this. If you don't want to, you can flip your paper over and there's plenty of space in the back there. Okay? So, converting. Because it would make sense that with rectangular and polar, we're both kind of like doing the same thing, right? We are both rectangular coordinates, x and y's, and polar coordinates, r's and thetas, right? It would make sense that they're doing the same thing, so we should have a way to translate from one to the other, right? We should be able to convert from one to the other. And so here is kind of like how we're going to do that. And it will look familiar to you, I think. Okay, so let's think about what we were doing when we located point in the or using polar coordinates and stuff like that. So there's the pole. And there's our distance r we went out. And there's our angle theta that we did. Okay? And this located the point r comma theta. Okay, right? But this point, remember the pole is located at what coordinates? In rectangular coordinates? It's at 0, 0, the origin, right? This is the origin.
But here it's 0, anything. In
a sense, yeah. Mm-hmm. But it's also like the origin for our coordinate plane with rectangular coordinates. So to locate this point similarly, I would need to go out some distance x here, right? And then I would also have to figure out this vertical distance y that we went. What kind of shape have we created here? Yes, and specifically what kind of triangle? A right triangle, right? So how can we relate these pieces of information? Well, if I know the polar coordinates, I know r and theta. So in other words, I know the hypotenuse. I know the hypotenuse of the right triangle, and I know theta. How can we relate the hypotenuse and theta with y or x here to then solve for those values? What do we use? Sine or cosine. So sine of theta, oh my gosh, it's all coming together. Sine of theta will be equal to y over r, or the more typical way that we write that is y equals r times the sine of theta. I just multiplied the r to both sides there. Okay, multiply r to both sides, you get y equals r sine theta. Okay, and then, well, I guess I should do this, whatever, I'll do it over here. I kind of did it backwards, but okay. Cosine of theta then would be x over r, right, the adjacent leg over the hypotenuse. And so then, again, x equals r times the cosine of theta. Now, you might remember this. We did this, right? A couple units ago, we found rectangular coordinates, okay, on one of these rings. In fact, the ring of 1. What's the name we have for this ring that's got a radius of 1? It's the unit circle. So when we located coordinates on the unit circle, okay, we first used a very basic form of polar coordinates, okay, where r was always 1, and we just found all those different theta values. We found that polar coordinates, and we found all of the matching rectangular coordinates using sine and cosine. And you'll see here, right, for the unit circle, r is 1, and so that's where we get the r is cosine theta and y is sine of theta, right? How I always said that the x coordinate was like the cosine, the y coordinate was like the sine. Okay, that's a more specific form of this general formula here with x and y coordinates. Okay? So, let's try converting here. Convert from P to R. Polar to rectangular, right? I'm just trying to save space here. All right, so let's say the polar coordinate is 2 comma pi. Okay? We'll say that's polar. We want to know what are our rectangular coordinates going to be there. Okay. Well, we have our two little relationships here, right? X coordinate, the x rectangular coordinate will be equal to r times the cosine of theta. So x is going to equal 2 times cosine pi. And y will equal 2 times the sine of pi. Y is r sine theta. Okay. What's the cosine of pi? -1 times 2 will give us -2. What's the sine of pi? 0 times 2 will give us still 0. And so our coordinates are -2, 0. Which really should make sense, right? So let me show you why that should make sense here. Let's go back up to our little grid up here, okay? And let's locate 2 comma pi on the polar coordinate system here we've got. So pi, right? There's pi. and we're going to go 2 in that direction. 1, 2. Well, let's think about the location of this, right? If you think about the y, this is on the x-axis, right? If you can imagine, you can see the x-axis here, and there's the y-axis here. So this point is on the x-axis, therefore the y-coordinate will be 0, right? And it's 2 units from the pole, which is the same as the origin. So going 2 this way is -2, right? So anytime you're at like pi or 3 pi over 2 or pi over 2 or 0 or 2 pi, something like that, right? Those are pretty easy to find because they're just like straight up and down or left and right from the pole. It gets a little bit trickier, right, when you'll have like less nice numbers, I guess I'll say, when you start talking about like things on the rings here, okay, within the quadrants and stuff. Okay? And of course, we can also convert from rectangular to polar as well. Zoom out a bit. Yeah. Oh, sorry. Yeah. You want to get this right there? Okay. But I think we'll hold off on converting from polar to rectangular, or rectangular to polar for another time. Okay. So, let me get you guys started on your assignment then. Okay. If you need additional graph paper for the polar stuff, well, tomorrow we'll do polar graphing, like the graphing, like functions and stuff like that. Well, I don't know if I call them functions. We'll graph polar equations, I guess we'll say. If you want a sneak peek of graphing polar equations, all right, if you go to your calculators and change the mode, I know I'm changing it all up on you and stuff like that. If you go to your calculators and change from func to pole, you'll see now that r is like our y, r is like our dependent variable, and then theta is our independent variable. Okay, and if you press, like theta there, okay, you'll see the theta. Like if you press the X button or the T button, a theta shows up instead here. Okay, and so you can like see some stuff there. Look at that. That's just theta. Okay, and of course you can use like sine of theta if you want to. Okay. And you can play around here. You can put in like coefficients and stuff like that, and it creates kind of interesting things. Let me see if I can get something more interesting. There we go. Look at that. Oh, spirography here. Let me try and make it bigger. There we go. Okay. Yeah. How crazy is that? Okay. So there. Let me see if I can make it 7. Let's try that. Yeah, so you see, you can create all sorts of crazy things. All right. So anyway, something to think about there. Let me see if I do it this way.
That's cool.
Yeah. Okay. And again, this will start to make more sense as we go about things. But we won't do any things necessarily this crazy. But we'll do some weird graphs for sure. Okay. So anywho,
That's funny.
let me get you guys started on your assignment. Like I said.
You just walked in laughing.
Nice.
Shouldn't tell him it was my name. He would have just not asked any questions.
Go ahead.
Thank you.
All right. Now that the excitement's over here, we'll get you guys your assignment there. So 5, 7, 11, 19, 23, 37, and 43. Okay? So 5, 7, 11, 19, 23, 37, 43. All right? I have additional big graphs for you if you want to use big graphs, but I also have small graphs for you somewhere back here.
If we use a big graph, can we use the same one? And then
If you want to use the same ones like the back or something like that, that's fine. And I also have small graphs for you here too. We'll be utilizing them tomorrow too. But yeah.
how did you get the black one?
How you
Other
want?
than that, we got a flower.
Oh, the flower. I got you. Hang on, I'll get you 1 second.
I showed her.
Oh, you did? Okay.
Mr. Rimmer, I need help with my calculator again.
Okay.
I really don't know. That's not
I'm gonna try and show you.
okay.
Is that okay?
Yeah, that's fine.
I'm gonna explain it to you.